Many ways to calculate the KD, ligand binding concentration to the protein by using different techniques like SPR or isothermal calorimetry, UV, other techniques. From NMR also we can calculate the KD. In this case, NMR will be calculating for the particular residues. If we are considering protein, particular residues, each residue can be fitted differently, different KD. And if you are using 1D NMR, like a small simple molecules, there also you can use particular peak, well resolved peak to fit the KD. So what we do, like we take up here, we can consider protein, and we can take a protein, and here I have like 100 micromolar protein, and then what I do, I titrate the ligand to my protein. Then I see the change in chemical shift of particular residue, so I extracted the chemical shift of that change in chemical shift of the particular residue at here. So when we plot this, you get the concentration versus the chemical shift of the particular residue. So this is the how we get. So from this we can get KD by using this equation here. So delta observed is, which means what we have here, and the delta maximum is the maximum change in chemical shift. Here also we have. Then ET means it's a total protein concentration, and LT is the total ligand concentration. So I will give the reference paper for this in the description. By using this formula we can fit KD, and also there are different formulas for different exchange, different like strong interactions and very exchangeable interactions. And for hydrophobic, I think we'll have different equations. So you can go through the link and find out which equation suits better. So before fitting the KD, what we have to do, we have to calculate the theoretical change in chemical shifts by using this same our chemical shifts. So what we do here, you can put the same thing you can use, like to calculate the chemical shifts you can use protein concentration, ligand concentration, and KD. KD I put just 1 at the moment, and CSP max is our this value, then maximum. So in this case, just I put theoretical calculation at the same formula is total protein concentration, this, and I do want to fix this, so I put a dollar sign. I don't want always changing this value. Then I put the protein, delta max, right? First I put CSP max, same protein, I put dollar, and then we add total protein concentration. So this also has to be fixed, not variable. Then plus the ligand concentration. The ligand concentration is this one, B6, and this is variable, so we don't put any dollar sign. And plus KD. KD is this, and this is also, it's not variable in the sense the columns, so we fix that particular place like I7. So we finished our first, the delta max and total protein concentration and ligand concentration and KD. Then minus, we put square root on the top later, so this delta, square it, and then total protein concentration, again the dollar, total protein concentration plus again the ligand concentration is variable plus the same you have to repeat here. Then I7. I7. So again, and close the bracket, and you can see here this is under the square root, and all these parameters are added plus squared. So I put square. Then this square, again I have the next equation, so I just close the bracket to make it a separate parameter. Then I have minus 4 and total protein concentration, minus 4. Then I add protein concentration into ligand concentration. So this is my star protein concentration, this dollar into ligand concentration. This is variable, right? So this whole term, this whole term is under the square root. So what I do, I bracket here and I close this whole term. The first term is under square, so it's here. Then minus 4 protein concentration and ligand concentration, and everything is under square root. So what I do, I put square root, and now whole this term is divided by 2 into protein concentration, but this one is excluded, so just we have to divide this term by 2 into protein concentration. So what I do, I put a bracket and this bracket overall and divided by 2 into protein concentration. Yes, so this is our equation. So again you can see that this is delta max is here, the maximum change in chemical shifts, and then this one is multiplied. You can put the star, or it's enough, like you don't need to put star also. And here this for term, the protein concentration plus ligand concentration plus Kd. So the delta I6 is protein concentration, ligand concentration, it's here, it's variable, so we don't put dollar sign. And then I7 is our Kd. Kd just I put 1 for time being, because which we need to fit later to have some values here. Then minus the same term is squared here, and here you can see the same term, whatever we have squared. I close the bracket, then minus 4 into total protein concentration and ligand concentration. So total protein concentration is here and ligand concentration is here. Then whole this term is square root, so I put squared 0.5, it's 1 divided by 2. Then whole this term is divided by 2 into total protein concentration. So I added 2 into protein concentration. So now we have a calculated chemical shift. Just enter. So this will be our calculated CSP. Okay, so I have now, then I calculate this. This is our calculated CSP, and this is our observed, like determined from NMR experiment. So now what I do, I include this also in the plot. Now you can see it's very lean, right? So it's not fitted. Once we have a proper fitting, the orange curves try to match the experimental one. So to do that, what we have to do, we have to calculate the square of this calculated and this one to minimize, to fit the proper one. So what we do, we can put this one, you can say R square, sorry, or we can like just type r square. Here what I do, I put this minus experimental minus calculated, square this. Then we calculated the difference between calculated and this one and squared. So we take sum of the calculated parameter, sum of this whole parameter, close the bracket, and multiply by some high number, because we are dealing with very small change in chemical shift like 0.09 or something, and r square sum is also very small number. So to minimize that number even more small, so sometimes the program also gives some wrong information. So to avoid that, we can multiply with the high number to have a large number. Then we can easily identify how we can fit the value. So what I do, I transfer it here. So this will be our sum square into that some number, random number you can do. So once we have this, now we are ready to fit. To fit the KD in Excel, we need to have a solver. Solver, usually if you go here and you will find it here. Otherwise you have to add, this is the add-on, free add-on for the Excel. So you can go to the Excel add-ons and you can select the solver. So once you have this solver, so what you do, you can click the solver, right? So this is our solver. Set objective. So what we want to do, we want to minimize this square. If we minimize this square, which means the experimental, this is experimental and this is theoretical, so the difference is too large now. If we want to have a proper one, the difference should be very less. For example, before fitting I can show you something, like let's close this. Now I have KD1, and if you expect KD is very the smaller one, like 0.5, and still it's no, you can put a pen. Oh, not changing. Maybe it may be a different value. We can try to fit and get that value. So now we have to minimize this, right? So let's try that. So go to solver, and I want to minimize the sum of squares, and here you select minimum by changing the KD and CSP max. You can fix the CSP max. There is no much difference if you have like proper curve. Just let's see. I selected these two equations. So I'm changing some, like minimizing sum of squares and changing the values of KD and CSP max, and just click solve. See, now I got this equation, it fitted. So as I was using in molar, so that's why it was not taking 2.5. It's very small KD. If I used this one,